In this section, we reconsider in detail the ideal gas temperature scale introduced in this section before in the previous chapter 3, section 6. This scale is based on the observation that as the pressure of a real gas approaches zero, its equation of state approaches that of an ideal gas. It said that PART14. It will be shown that the ideal gas temperature scale satisfies the definition of thermodynamics temperature scale, which says that QH on QL, TH on TL. But first, let us consider how an ideal gas might be used to measure temperature in a constant volume gas thermometer. Shown geometrically in this picture. Consider this picture for us. In this picture, consider an ideal gas used to measure temperature in a constant volume gas thermometer. So we have a thermometer here. Let a gas bulb be placed in the location where the temperature is to measure. Here, gas bulb. And the mercury column be adjusted so that the level of mercury stands at the reference mark A. A is reference point. The volume of gas remains constant. Assume that the gas in the capillary tube is at the same temperature as the gas in the bulb. The pressure of the gas, which is indicated by the height L of the mercury column, is measured the temperature L related to pressure so for the let the pressure that is associated with the temperature of triple point of the water also be measured, and let us designate the pressure P triple. Then from the definition of an ideal gas, any other temperature T could be determined from a pressure measurement P by the certain relation T equals to P on the P triple. In fact, it is the T on In a certain constant volume ideal gas thermometer, we have this relation for temperature and pressure. From a practical point of view, we have the problem that no gas behaves exactly like an ideal gas. However, we do know that as the pressure approaches zero, the behavior of all gases approaches that of an ideal gas. Suppose then that a series of measurements is made with varying amount of gas in the gas bulb. This means that the pressure measured at the triple point and also the pressure at any other temperature as shown in this relation is plotted against the pressure of gas with the bulb at the triple point of water, a curve obtained as 4T on T triple point, P on P triple point for gas temperature, and we have this sketch. So if indicated temperature as shown in this graph obtained by assuming the gas is ideal is plotted against the pressure of gas within the bulb at the triple point from the previous picture, which we have the picture also here. Triple point of the bulb at the triple point of the water as shown in the picture. The bulb is here. A curve like the one shown in this picture is obtained. When this curve is extrapolated to zero pressure, the correct ideal gas temperature is obtained. This point. Different curves may be result from different gases, but they would be indicated the same temperature as P equals to 0. As shown in this picture, for various gases, we have the same indicated temperature and pressure equals to 0. We have outlined only the general feature of the principle for measuring temperature on the ideal gas scale of the temperature. Precision work in this field is difficult and laborious, and there are only a few laboratories in the world where such work is carried out. The International Temperature Scale, which was mentioned in Chapter 2, closely approximates the thermodynamic temperature scale. The International Temperature Scale closely approximates the temperature scale, thermodynamic scale. Which was defined in the discussion of the Carnot cycle and the second law. We now demonstrate that the ideal gas temperature scales, in fact, identical to the thermodynamic temperature scale, the ideal gas temperature scale. We have also Our objective can be achieved by using an ideal gas as the working fluid for a Carnot cycle heat engine, and they analyzes the four process heat make up the cycle. The four states in this picture our objective can be achieved by using an ideal gas as the working fluid for a Carnot cycle heat engine, and analyzes the four processes that make up the cycle. The four state point 1, 2, 3, and 4 in this picture, and the four processes are shown. Four state and four process. For convenience, let us consider a unit mass of gas inside the cylinder. Now for each of the four processes, the reversible work done at the moving boundary is given as this relation. PdV. Similarly, for each process, the gas behavior is the ideal gas, so we have P equals to RT. And the internal energy change for the ideal gas is CV00, denotes the ideal gas, dt. For this four process, assuming no change in kinetic potential energies or kinetic potential energies, the phase law can be written as delta Q delta U plus delta W. Substituting the three previous expressions into the equation, we can obtain, we have this relation, delta W here, and also we have a relation for P from this equation. We can conclude that delta Q CV0 dt plus RT on dV. The shape of the two isothermal processes shown in the figure. Since PV is constant in each case, the process 1 from 2 is an expansion, and TH, the process expansion at TH. Such that V2 is larger than V1. Similarly, the process V2 greater than V1 for an expansion. The process 3 to 4 is compression at T L, and V3 greater than V4. The adiabatic process, we have an adiabatic process from 2 to 3. Adiabatic process is an expansion from TH to TL. As shown, this is expansion because the volume is increased. While the adiabatic process 4 to 1 is a compression from TL to TH. With a decrease in a specific value. The area below each process line represents the work for that process. This process, for example, for 1 to 2, we have an area that shows the work for 1 and 2 process, this area, and also we have an area here, we have various areas. We now proceed to integrate the equation, as we have delta Q CV0 dt plus RT on B dV. With integration, we have CV0 dt plus we now proceed to integrate this equation. So we have QH for process 1 to second. Let me provide the picture again. The process 1 to 2. The integration of the Q is QH because the QH is related to the high temperature process. CV0 dt plus RTB dV. This is T constant as shown in the picture. So the first one is 0, QH is, and with integration we have RTH B second on V1. For the process we have an adiabatic process. So delta Q equals to 0. The relation is cv0 dt plus rt on v dv. And we can also, if we divide it with t before integration, we can obtain also these relations. dt plus integration of r on v dv. For an ideal gas, cv0 constant and r also constant. We can calculate that then. Nice. For the isothermal heat rejection process 3 to 4, we had the isothermal compression, QL 3Q4 the isothermal 0 and RTL LN V4, the second V4 on V3. So QL is RTL LN, the second volume, in this case 4 on 3, and also we have another adiabatic process for 2, 3 adiabatic. Zero equals to CV0 on T dt plus R ln V1 on V4. Consequently, we can obtain this relation for V3 on V2, V4 on V1, or we can write V3 on V4. So we can conclude that the thermodynamics temperature scale RTH LN RTL V4 on V3 on V4 TH on TL. Ideal versus real machine in the next description.